To astronomer Edwin Hubble and others, scientists have known since 1929 that our universe is expanding. Its current rate of expansion is called Hubble's constant, or h-naught. There are two leading ways to measure h-naught, and for 15 years, they more or less agreed with one another. Not anymore, and that's a big deal. Here's why. In the standard model of cosmology, h-naught is a crucial ingredient, right up there with the speed of light. H-naught factors into everything we know about the universe, how old it is, how big it is, what it's made of. If h-naught is tweaked, we get a different age of the universe, different relative amounts of matter, dark energy, and so on. Unlike the speed of light, however, scientists can't measure h-naught in the laboratory. Instead, h-naught has to be inferred from observations of the universe. One way scientists have measured h-naught is to use observations of type 1a supernovae combined with their host galaxy's redshifts. Each 1a supernova releases roughly the same amount of light when it explodes. Measuring the amount of light we receive from a 1a supernova tells us its distance. Measuring an object's redshift, or its increase in wavelength, tells us how fast that object is moving away from Earth. Researchers use many 1a supernovae as distance markers, measuring objects in our local universe, then moving out to get a measurement of the universe's rate of expansion. The other h-naught measurement technique looks at the cosmic microwave background, or CMB, the afterglow from the Big Bang itself. The early universe was hot and dense. Light couldn't travel freely through space. As the universe cooled, the photons were released. This radiation left an imprint, providing insights into the composition of the universe at that time. The CMB can be used to make measurements from the early universe, such as the density of dark matter and dark energy. Those measurements can be combined with the model of the evolution of the universe, allowing researchers to infer the rate of expansion of the universe, or Hubble's constant. As these two camps have improved their abilities to measure h-naught, it has become clear that they disagree. A recent study using the first method yielded an 8% greater expansion rate than the second method's result. Now scientists are asking, are we missing something? Of h-naught. Maybe the standard model of cosmology, which predicts agreement, is wrong. That would send researchers on an exciting search for a new model of the cosmos. Do we really know what makes up all of the radiation in the Big Bang, wonders Friedman? Is there a new kind of particle we aren't accounting for? Or are dark energies or dark matter's properties changing over time?
It's long been known that particles such as electrons have a mirror twin with opposite charge. These inhabit the strange world of antimatter, loved of science fiction writers. In this case, the antimatter partner of an electron is a positron. In the presence of an electric field, they move in opposite directions. But CERN will be looking for an even stranger pairing. At the beginning of our universe, a minute blob of time and space, far smaller than an atom, began to expand as a way of dissipating its extreme energy. Such three-dimensional spatial expansion that happens everywhere all around us is well represented by this two-dimensional surface of a balloon that is stretching as it's been blown up. The Big Bang into pre-existing space is now seen as the big stretch of space itself. After a moment of extraordinarily fast expansion, the blob seems to have contained a plasma of particles. On further stretching, the quarks and gluons condensed into protons and antiprotons, which almost annihilated each other. But not quite. The few protons left over formed the basis of the universe we now live in.
At this moment, the Big Bang, pure energy, is released. In a furnace of heat, space expands at incredible speed. In the tiniest fraction of a second, our universe is born. This is the deepest of all mysteries. Some of the energy now condenses into matter. At this moment, all the particles that make up our universe are created. Some we do not understand yet. Among the others are incredibly small quarks, electrons, neutrinos, particles that will make everything we know, including you.
The universe, as we know it, should not exist. Scientists working at CERN, the European Organization for Nuclear Research, have said, after performing the most precise experiments on antiprotons that have ever been carried out, researchers have discovered a perfect symmetry in nature. One of the big questions about the universe is how the first matter formed after the Big Bang, because particles and antiparticles annihilate one another when they come into contact. If there were exactly equal measures of both, the universe wouldn't exist, at least not in the form we see it today. As such, there must be an imbalance between particles and antiparticles in nature, even if it is only by the tiniest fraction. But this is not the case. All experiments designed to find this asymmetry have come up blank. This is also true of the latest experiments, which were recently carried out at CERN by an international team of researchers. All of our observations find a complete symmetry between matter and antimatter, which is why the universe should not actually exist. In the study, researchers used antiprotons that have been isolated. The antiprotons were measured using the interaction of two traps that use electrical and magnetic fields to capture them. The team was able to measure the magnetic force of the antiprotons to a level that is 350 times more precise than ever been done before. If there was an imbalance between protons and antiprotons, this level of precision would find it. After finding no asymmetry between particles and antiparticles, the researchers will now work to develop even higher precision measurements of protons and antiprotons to improve on the latest findings. An asymmetry must exist here somewhere, but we simply cannot find it. What is the source of the symmetry break during the Big Bang? That is the big question. One more step in our journey to understanding the fabric of the universe. The more we understand, the more we become humble to realize the grand scheme of this universe. Yet, we are no more closer in understanding the basic fundamental questions. What caused the Big Bang? What is the origin of life? Does God exist?
فإذا برق البصر
So when vision is dazzled,
وخسف القمر
and the moon darkens,
وجمع الشمس والقمر
and the sun and the moon are joined,
يقول الإنسان يومئذ أين المفر
man will say on that day, where is the place of escape?
كلا لا وزر
No, there is no refuge.
إلى ربك يومئذ المستقر
To your Lord that day is the place.
كل شيء حي أفلا يؤمنون
Have those who disbelieved not considered that the heavens and the earth were a joined entity, and we separated them and made from water every living thing? Then will they not believe?
وجعلنا في الأرض رواسي أن تميد بهم وجعلنا فيها فجاجا سبلا لعلهم يهتدون.
And we placed within the earth firmly set mountains, lest it should shift with them, and we made therein mountain passes as roads that they might be guided.
وجعلنا السماء سقفا محفوظا وهم عن آياتها معرضون.
And we made the sky a protected ceiling, but they from its signs are turning away.
وهو الذي خلق الليل والنهار والشمس والقمر كل في فلك يسبحون.
And it is He who created the night and the day and the sun and the moon. All heavenly bodies in an orbit are swimming. And the heaven we constructed with strength, and indeed we are its expander.
وَالْأَرْضَ فَرَشْنَاهَا فَنِعْمَ الْمَاهِدُونَ.
And the earth we have spread out, and excellent is the preparer. Be grieved by the greatest terror, and the angels will meet them saying, This is your day which you have been promised.
يوم نطوي السماء كطي السجل للكتب كما بدأنا أول خلق نعيده وعدا علينا إنا كنا فاعلين.
The day when we will fold the heaven like the folding of a written sheet for the records. As we began the first creation, we will repeat it.